Okay, so in this particular problem, we have a robot is going to go around this maze all over the place. It's equally likely to take any of these exits. And the time interval between the robot entering and leaving the room is the same for all transitions. So we want to find a transition matrix. So when I make a transition matrix, I always go in this direction. This is the current, and this is the future state. And so that's what I have to think about. So if I start here at A, I am going to stay in A, so it just is going to be 0. Now, if I want to go to B, there's 2 possibilities, but there's 2 out of 2 in total. C, there's 0 ways, and D, there's 0 ways. When I look at, if I am now sitting in B, if I'm sitting here, I have 2 ways. I have in total 4 different ways. 2 of them I could get to A, 0. 1 of them I can get to C out of 4, and 1 of those 4 ways I can get to D. And similarly for C, I have 2 options. 1 of those 2 goes to B, and the other goes to D. I cannot get from C to A. And similarly for D, I have here and here, so I have 1 out of the 2, 1 out of the 2, and 0 options here. And so this here is my transition matrix. And so we will often call this here, as opposed to 2, we're going to make that a 1, and so on and so forth. Then, as it says, we want to we put the robot in the maze and leave it to move around for a period of time, find the probabilities in room B when the scientist returns. Well, if I call this matrix T, well, I'm going to find T to the power infinity to find out the steady state matrix. And when I do that in my calculator, I just put in here a big number like 20 or maybe 40. I'll end up with 0.2, 0.4, 0.2, and 0.2. And when I have it, if I want to find that I'm going to be in room B, well, that's clearly 0.4 is the probability that the robot will be in room B.